Okay, good morning. Can anyone hear my voice?
Yeah, Professor.
Thank you. Okay. 12 of you. Could be okay. Right? So I think according to the the last lecture, I think I asked you to how to say to watch the previous clips on the free vibration, right? Last year lectures, I think, and I thought that would explain you about the free vibration and also provide you some information about the handout I provide, which explain the first case, maybe the free vibration and the very small damping, a positive small damping, which we call the underdamped system. So today I would like to continue with that explanation. But before I go into the detail, let me start with the very beginning of the equation of motions, equation number 1, which I think we all done with the equilibriums before. And if you look at the system, a single degree freedom system, where you represent your bridge, your building with the only one movement degree of freedom. For the building, most of the time we look at the load of the structure of the building. For the bridge, some very interest on the deflection, the movement of the midspan motion. And we try to get the behavior or the solution or the maximum vibration of those quantities. To do so, we represent that or those real buildings and bridges by one physical degree freedom system. A physical system which contain only one degree freedom. Right? For the building, for the bridge, we represent with the same thing. One mass, one stiffness, and one damping. This spin mass system, as in this figure, I think, can represent the motion, horizontal motion. But you can do very similar with the vertical motion as well. Therefore, both of the system, no matter it's moved in the horizontal directions or in the vertical directions, that's share with the same equations of motions, same mathematical equations as in equation number 1 based on the equilibriums. When we apply the force equilibrium and assume there's no force, this is the case where we are considering. I would say, let me use the pink is good. We assume this. There's no external force on the system. And we try to calculate or derive the equations of motion. And I hope you can enjoy with equation number 1. Everybody get or obtain these equations to guarantee that in every instant of time, the force in the system are in equilibriums. And in this equation, explain that the initial force combined with the damping force, combined with the stiffness force, would be equal to the external physical force Ft, and is equal to 0. The way to define the direction of each force, I think we have learned before. Therefore, I don't want to go into the detail again. Okay. In the shear force, this is the first term. Mx double dot in the shear force. Cx dot represent the damping force. And the Kx represent the stiffness force or the spring force. Three of the forces need to be, how to say, some of them need to be equal to 0. Okay. And we found by looking to these mathematical equations closely, we found this is a second order differential equation. If the mass, the damping, the stiffness, M, C, and K are the parameters that is represent mass, damping, stiffness. If we assume they are constant, this assumption is pretty good. Most of the time, mass is constant, the damping as well, and the stiffness. Actually, the stiffness and the mass is quite, mass is very constant. Stiffness is sometimes when you go with a very large motion, maybe you might expect that the structure might exhibit behave like a non-linearities, right? A little bit non-linearities. But the damping is quite strong, non-linear behavior or property characteristic. However, in these lectures, in this study, we will assume all these three terms be a constant. M, C, and K, one of them constant, not change with time. Okay. Therefore, the only parameter unknown to us is about the displacement x, x dot, and x double dot. And this form what we call the second order differential equations. To solve this equation, I think you should learn already about the assumed form of the equation number 2. Since the form of the second order differential equation is very, very popular and we know what are the solutions, at least the form of them. Therefore, we're pretty sure that the form of the solution should be in the form of equation number 2. Therefore, we assume this form in equation number 2 and introduce into equation number 1. When you introduce 2 back into equation number 1, we found equation number 3, something like this, right? And I think you should already know about the possibility, 3 possibilities of the system characteristic. Because the S, which indicate the roots of the characteristic equations of these second order differential equations, they show the 3 possibilities of the value of the number of S, depending on the damping ratio. What is the damping ratio? The damping ratio is well defined as in this equation, right? Per psi, I call it per psi, equal to the damping coefficient C over 2m omega. Okay. And this is called the damping ratio. Most of the building has the damping. And every building has a certain value of per psi. We look at this equation number 5 and we found that the first possibility we would like to explore is when the per psi is a positive number and less than 1. And I think I already asked you to watch the clip that I have discussed with your senior last year about this topic. And it shows that the solution when the damping ratio is 1, correct, less than 1. is equation number 13. It shows some oscillations that the solution x equal to the big big X multiplied with the e to the power minus plus sine omega t and multiply with the sine omega t minus phi. A big capital X is a kind of one of the what they call the constant. Solving the second order differential equation, you should keep in mind that the solution, the general form of the solution, should be contained to arbitrary constant. And this one, equation number 13, the first arbitrary constant, I think it is the big X. And the second arbitrary constant is the phi. So when you have the two arbitrary constants, you can take in care the two initial conditions. When we're talking about the initial conditions, we look at the system without any external force. So the first question comes to our mind that, oh, how the building move if you have no force acting on that? The answer is, even though the system don't have the external force, F equal to 0, no doubt, there's no external force, this one, right? F equal to 0, Ft. But how the building still move without any force? The answer is, there might be some initial conditions on the system. For example, your system might subject it to a kind of initial velocity. At time t equals to 0, your system might have some, how to call, the initial velocity resulting from a certain impact force or some impact from another system, or even the initial displacement. As the time t equal to 0, maybe your system already have some initial displacement of 2 centimeter, 3 centimeter. Those might be some possibility of the initial displacement, initial velocity, or the combinations of them. However, the system that we often ask for, like this, the single degree freedom system, we are talking about the initial of X and X dot at time t equal to 0. If the initial displacement 0, initial velocity 0, external force 0, of course, no movement. I agree. But we are looking at the case that the initial conditions are not 0. Sometimes the initial displacement, when I say this is 0 mean t, right? Time equal to 0. So there's possibility that the initial condition of yours is not 0. And that is a case of free vibrations. See, there are two initial conditions that you need to take care, and that are those about the x0. Most of the time is like this: x0 and x dot 0 equal to a certain number given by you. To taking care of those two initial conditions, you need the big X and the phi, two parameters, two constants. These two constants, arbitrary constant, we're taking care of the two initial conditions that I mentioned before. Okay, therefore, the value of the big X and phi could be determined from the initial conditions. And if we assume the initial condition equal to x0, x dot 0, I think you can obtain something like this. Equation number 17. This is the value of the big X and phi. Okay. The behavior of this is quite interesting, and I think you already watched the video clip, and I just waiting and listen to your question. Maybe at the end of this today lecture, if you still have some question and some confusing, ask me and we will discuss with you. Logarithmic decrement as well, right? The natural frequency, this is very important. Why the frequency is important? Let me tell you some about this. When we design the building against the earthquake, for example, the design code, they will ask you as a designer to calculate the natural frequency of your building. The reason behind why they need the information about the natural frequency is because the earthquake force will depend on your natural frequency of your building. For example, in Bangkok, they call this is a response spectrum. The spectrum of the SA, I'm talking about the earthquake loading. The curve is something like this. Maybe I'm not sure. Just a 4 second, maybe. It's a 0 point something, right? 0.5 or something. Right? Normally, in every country, I do believe that the spectrum like this is very, very common. But it depends on what they call is the ground or the subground properties. In Bangkok, unluckily, we have a very thick layer of the clay, very soft clay, and therefore there's a magnification of the ground motion in very long period. The T is the period as in equation number 20. So even though you build the same building number 1 and building number 2, if your building share the same mass M, the value of the force called V1 and V2, the bed shear from the earthquake, will be different depending on what is period. Normally is a natural period, the first fundamental period of the first mode, mainly control the design. What is your period of vibration? We are talking about the frequency and period, okay? The two of them are just the T is equal to 1 over F, right? So you know the frequency, you know the period. It's just an inverse quantity of each other. If my building has the period like this, my building 1 is here, your building number 2 is there. Believe me, your building number 2 need to be designed with stronger earthquake force, larger earthquake force. My building number 1 will subject it to smaller earthquake force. You will learn in, I think, in next chapter, why it's like this. Why the frequency is so important. Why the period of building is controlled the force on me. That's why I would ask you, at least at this moment, please try to remember or imagine this. You should be able to feel how the frequency of the building or the period of the building change when you're changing the mass, when you're changing the stiffness, when you're changing the damping. And look at this equation number 19 and 20. I do believe that is really easy to remember. I always remember something like this. Omega equal to square root K over M, something like this, right? And from the omega, you can change into the circular frequency by saying that the omega is equal to 2 pi f. And this 2 pi f, in fact, is equal to 2 pi over period t, something like this, right? So every quantity about the frequency of the period related with the stiffness and the mass. Increasing the stiffness, the frequencies become higher. Increasing the stiffness 4 times, the frequency increasing 2 times. Increasing the mass will reduce the frequency. Increasing the mass 4 times will reduce the frequency 2 times. Something like this. Or even in the term of the period, you should at least, at this moment, I ask you to at least feel the frequency, feel the period of the structure. At least in your mind or your understanding, you should be able to forecast if your system or your buildings or your structure, the frequency or the period of them will change when you change the mass or the stiffness. At least you should know about the directions, the tendency, whether it will increase or will reduce, larger or smaller, faster or slower, frequency or speed. I'm sorry, the period. Okay, so keep in mind, yeah, it's quite important in which is control your behavior of the building. And the reason why the frequency and the period is quite important and very strong related with the external force, level of the force, I think it will explain to you on the next chapter. Okay. So today, we will move on the 3.2, right? Where the critical dam system and the overdam system will discuss. Going back to the 3 possibilities again, when I solve or you solve the free vibration system, equation number 5, see this characteristic root, right? We consider already the case of 3.1, where the damping of the psi less than 1. But if the psi is exactly equal to 1, if the psi exactly equal to 1, what's going to happen? Let me try this, right? You can imagine this term would be 0. I'm sorry. When psi exactly equal to 1. Right? And the S will be something like omega. S will equal to omega according to equation number 5. But let me look at this. 3.2. Sorry, minus omega. If the damping ratio of the system equation number 5 is equal to 1, it is evident that the term in the square root becomes 0, and then the root of the system reduced to 1, which is a real negative, as in equation number 21. If we introduce number 21, right, into equation, I think number 4 maybe, the tangent displacement solution we obtain as in equation number 22. Okay. This one is a kind of the mathematics stuff in which actually we should have S1 and S2. Remember, this is a second order differential equations. So I need the two roots of this to contain two arbitrary constants, to taking care of two initial conditions that we mentioned before. But in 21, they're telling things differently. They show that the only one root in the S. Therefore, I forgot the name of these mathematicians. I'm sorry, I forgot his name. They proposed the thing like this, something like, okay, you introduce S into U and you find another independent root and on your solution, and that one of the possibility is introduce the term something like this, A2T, the constant multiplied with the time T like this. Therefore, the normal form of the solution xt can be represented as in equation number 22. You see, now you have A1 and A2 as two arbitrary constant, and it's okay for this. Introduce 22 back into the, I think the equation of motion is lead to 23, where the xt, I'm sorry, this one is already introduced from 22 to 23. Here to there, you introduce the initial conditions. So. You introduce the initial condition where you say x0 equal to this term and the x dot 0 equal to x dot 0. Okay, by introduce these two initial conditions, you obtain 23. And equation number 23 is a time function, of course. In front of the parentheses, you can see the exponential term again, e to the power minus omega t. So this one is we have some we have like a decay function, right? It will reduce with time. When t equal to 0, this term equal to 1, and when you increase time t from 0 to 1 to 2 to 3, the term becomes smaller, smaller, smaller. And when t equal to infinity, you can imagine this is about 0, close to 0 or approach 0. But in the parenthesis of the 23, the term shows something like a constant multiplied with the time t. So this is just the linear function, the time linear term function, right? But this has contained, how to say, let me draw you this so that you can imagine and follow me. This can be x0 plus x0 omega plus x dot 0, all of them multiplied with time t, right? So this function is a time function, linear time function. Increase or decrease is depending on the slope here, right? the term here, whether this term is positive or negative. If this term, this is a slope of a linear function. If this term is a positive, you will increase with time, right? The value. But if it's negative, it will decrease or reduce with time. Therefore, the combination of the term as in 23 becomes something like this decay curve, the blue line. And when I plot this, please remember the initial condition is pretty easy when you look at the plotting like this. For example, here, let me zoom in a little bit and look at this initial, the red color may be better. Look at the time t equal to 0. I can tell you the plotting here, I assume something like this. X0 equal to 1, right? Remember, x is the time, this is the x of time t, the unit may be meters or any displacement unit. The velocity is what? I don't know whether what the value is, but at least I know about this slope. You know that the slope of the displacement history telling you about the velocity, right? Therefore, here, if the slope is accurately determined, you can tell that it's a positive number. I don't know whether it's a 2, 3, 4. I don't know the exact number, but it's positive. It's not negative. It's a positive velocity at the time t equal to 0. And with this initial displacement equal to 1, and the velocity is a positive number, it have the plotting of the blue line. I remember, right, I need the pink line here and plot right down to show you is because many discussion with my previous student, they found that when I say, okay, there is no sine term, right? There's no sine and no cosine term. The last one in equation number, again, number what? 23. Contain no sine and cosine term, therefore you cannot expect the changing of the sign convention from positive to negative, with time. When you have the sine and cosine term, it's very interesting in which your solution will change the sign convention from positive to negative, depending on the angle, right, inside the sine and cosine. But 23, there are no sine and cosine terms. Therefore, we said this system, the critical dam system here now, contain no oscillations, no vibration back and forth like under dam system. This critical dam system has no oscillation. But when I say no oscillation, it doesn't mean your vibration or your displacement is always in the same sign for all the time. For example, in the blue line, you can see that all the time x is positive number. Your displacement is always positive in the blue line plotting. For the critical dam system, it might make you confused when I say, actually, the critical dam system like this can have a positive and negative vibration. They can change the displacement from positive to negative. You may confuse, why? because there's no sine and cosine term. Right? You can change the sign convention from positive to negative. That's why I need the plotting of the pink to show you. The plotting of the pink telling me that if the initial displacement, for example, in this case is 0.x0 could be something like a 0.4, right? But my x dot is something special, is the very large negative. Very large negative. Slope here is negative, right? Therefore, you see the vibration is something like it's not go like this. Even though I put your team, it's not go like this. Like the left, no, never happen. If we go with the pink dotted line, change to positive to negative and then go to 0, like this. Look at the mathematics. The first term, I mean this exponential term, is always positive, right? But these two terms, maybe look at here, it's better. I can do the changing of the sign by, for example, x0 to be a positive number, but the slope is negative. If I do the thing like that, when the time increasing, the negative number, negative value will be come over positive number and it can change from positive to negative. You play around with this mathematics, it's not so difficult. But please remember, even though it said here, no oscillations occur, but it doesn't tell you that you cannot change from the positive to negative displacement. You can change from positive to negative, but you can change just one time. Then go to 0. You see at the pink dotted line. But if you're talking about the oscillation, actually oscillation is like this. The green one maybe. You see, if you be an oscillator thing, it could be something like this. Positive, negative, positive, negative, positive, negative, like this, right? They're changing from positive to negative, to positive to negative, to positive to negative. Many times, that's why we call oscillation. Not just one time. Okay? So please remember this. The last one is the overdamped system. 3.2 is the critical damped system, the system in which the damping is exactly, damping ratio per sign, exactly equal to 1. But when the damping or the precise of your system is greater than 1, the thing of equation number 5 will lead to equation number 24. We introduce the precise greater than 1. And what we found is the solution become the complex conjugate. You contain the term of the imaginary number. You know about the A plus BI, right? When you're talking about the real and imaginary number, this is a complex number. You contain something like a square root of -1 here. And that is, how to say, quite difficult now. When your system contains a complex conjugate like this in your solution is, the solution will take the form like what is an imaginary number? Remember, the precise term here is greater than 1, right? When your precise greater than 1, the precise square is always greater than 1 for sure, right? And therefore it's -1. I'm sorry. Why is there like this? This one is not the engineering number. I'm sorry. Let me go back in equation 5. Engineering number is the case where you have the underdamped system, right? Number 5 again. Yeah. Let me explain you again. Previously, my explanation is not true. I have a mistake. I thought this one is a 1 minute per sine, right? But it actually is per sine square minus 1. Therefore, when the per sine square here greater than 1, this become a real number, just a real number, right? When you take the square root. Okay, because inside the square root is positive number, so it's easy, right? Take the square root out, and your solution in this case, the overdamped system, 3.3. Just the two roots or unequal real roots. You have two roots, but they are the real number, not complex number, sorry. Complex number is the case 3.1. Just the real roots, real number, but they are different in terms of the quantities. And that will lead to equation number 25 when you considering the two initial conditions, A1 and A2. But now, look at the form of equation 25. It's look like the sine cosine again, but it's the hyperbolic functions, sine hyperbolic and cosine hyperbolic. The term of exponential look the same, exactly the same with the previous case. You have the e to the power minus per sine omega t is quite common for every system, the three system we are talking about. But there has in the parentheses is a hyperbolic sine and hyperbolic cosine, the combination of these two terms. Okay, so it's depend on the initial conditions. You can calculate what's gonna be the A1 and what's gonna be the A number 2, A sub 1 and A sub 2. It depend on the initial condition you provide. Okay, so the plotting of the 25 is look very similar. I would say very similar, even though the time functions are different. But 25 and 23and 23, even though the form is totally different, but when we plotting the curve from the same initial conditions, we found it look very similar. So that's why before I telling you about this, I would like to quiz you today using the Padlet, okay? Okay, I will provide you the link of the Padlet and telling me the answer of this question. Look at this plot. In this plot, you have the three curves. The red color, the green color, and the blue color. I'm not so sure whether you understand it correctly or not, but for sure is the red color is the 3.1, the underdamped system, where the per sine less than 1. Okay, remember you have the three systems depending on the per sine. The first system is the underdamped system, as we have discussed in 3.1 before. The second, 3.2, we discussed about the critical dam system. And the 3.3, we are talking about the over dam system. This is the case per side less than 1. The side exactly equal to 1 and the side greater than 1. Something like this, right? My quiz, just asking you, the left one is that shows some oscillation from the initial condition. I think this is I guess my plot is x0 equal to 1 and x dot 0 equal to 0. No initial velocity. Just the initial displacement velocity is 0. Okay. And let the system go with this initial displacement of the unit 1. The red color, I do believe the red color is belong to the underdam system because it's contain oscillation. Remember, it's a sine cosine. But the critical dam system and the overdam system, I don't know which color is belong to these two. And I would like you to imagine or look at the mathematical solution 25 and 22 maybe. Imagine what is the critical dam system, the green or the blue, and what is the overdam system, the blue or the green. Just easy like this. You carefully look at this curve, this plotting, and telling me the critical dam system, which color it is? The overdam system, which color it is? For sure, you cannot say green and green. You cannot say blue and blue. I plot the tree system for you here in this plot. So the green need to belong to one of the critical or the overdam. And the remaining will be the blue. Okay. Any questions? I will tell the link to the Padlet link to you. You write down your ID and just say the red, the green, the blue, return back to me within maybe just the 3 minutes, right? Any questions? Otherwise, I will provide the link. Okay, I already create the link and provide to you. And in the Padlet, if you click on the link, you can see the example of the answer, right? Just telling me your ID and say 1 is equal to red, 2 is a critical dam system, 2 is the blue or green, you tell me that. And 3 is blue or green, is the overdam system, something like this one. Okay, I got one from your student. Okay, 2 of you answer me already.
Professor,
Yeah.
how to use this link? I need to register.
Huh?
Uh,
I don't think so. I just open public. So if you click the link, you will on the Padlet, and then you just you have the plus sign maybe in your, I don't know, you use a notebook or the telephone. You just click on the screen. They will tell you how to post something, and that's the way you provide me the answer.
I see 1 equal red, 2 equal.
Yeah. And you just click on that. It have the plus sign right in the bottom, light bottom. You see that?
Oh, okay.
Okay, you just press that,
Thank
and you tell
you.
me the answer. Good. Okay, you have 1 more minute.
Need to set my I need to set my ID student.
Yes. As the first row, okay, you're telling me your ID.
And press save. Thank you.
Okay, so I will close the system. It means that everybody need to answer me already, right? Okay, 15 of you. Good. Let me change to the set. Okay. I think it's quite good. Almost of you say number 1 is red, number 2 is green, and number 3, the overdam system, is blue. Only 1 or 2 of you is noticed. It's quite different. Therefore, your feeling is good. I would say that the critical dam system is green. The critical dam system is green. And the overdam system is blue. Okay? Only one of you or two of you said the critical dam is blue and the overdam is green. I noticed some of the feeling like this from my previous student. When we say overdam system and the critical dam system, even though the feeling of the damping will telling something that your system will go to zero faster, can dissipate the energy better. And that's why every engineer would like to have more and more damping in that system when you would like your system to have very small vibration. Damping is good to us. We need them. We need more and more damping to our system. But it doesn't tell that the critical damp system and overdamp system, the overdamp system have more damping. Therefore, some of you may feel they should go to zero or stop, the vibration should stop faster. We should not say so. In this case, the green belongs to the critical damp system. The blue belongs to overdamp system. It shows that the overdamp system has more damping, but they go to zero slower than the critical damp system. The reason why is like that? This is explained by mathematics, of course. If we look at the mathematics, the solution of the green and the blue, we found that if you have so many or too large value of damping, more than critical, the system will very inert. It's go very slow movement. Very slow movement because your damping is very, very large. And that's why they go to zero slower than the green. If I were the mechanical engineers who design the car suspensions or some what they call the aerospace or any structure or machine, they prefer the critical damping when they would like to drive the system, the machine, the vehicle to zero as fast as possible. The critical damp system is the best system to do that job. But if I concern something different, like I concern, for example, the small vibration and small accelerations, I need the system once they impact to the ground, even though it takes some time or take quite a long time to stop, but when the machine or the aerospace touch the moon, for example, I need my system to be a very small value of the impact acceleration. I don't want to damage my equipment in the aerospace when I touch the moon, and that will need a critical damping. I'm sorry, over damping. You will need the over damp system. Why is over damp system is better than the critical damp system in this case? Is because you look at the blue. If you go with the blue, it will guarantee you that the acceleration will smaller than the green. The displacement, when you perform the derivative, it becomes the velocity. And when you perform one more derivative, it becomes the acceleration, x double dot. And the x double dot of the blue is very small, comparing with the x double dot of the green and the red. So the system will stop very smooth, very, very smooth. You add more damping to the overdamped system, you gain this smooth wording. Your system become a very inert and smooth system. Very small inertia or impact on your equipment or devices in the aerospace, for example. When you touch something and you impact with something. So it depends on the application, right? Whether you need to stop the vibration very fast or you want to be a very smooth, you need to select and design your system accordingly to your target performance you want. But for civil engineers, I would say the green and the blue, we never have this in reality. In buildings, in bridges, we always have the lead under dam system. And I do believe that the most highest damping structure, civil structure, maybe the damping ratio per side is something close to 20 something, 30 something, 0.2, 0.3 only. We never has the system having the damping ratio greater than 0.5. I never found so. Okay, so the damping of our structure is something like a 20%, 30% maximum in actual situation. So the lead color is our case under dam system. And this is another system, number 4, maybe 3.4, where you have a negative damping. If you have the negative damping, is something like during the vibration, you gain more and more, larger and larger displacement with time. And the system is unstable, right? You can imagine that if you let the system go for just a certain time, they will destroy themselves. They destroy themselves because the displacement become infinity. And we don't really have this. But some engineer or some researcher, if you remember the Tacoma Bridge, the bridge that collapsed under the wind, they try to explain that system to have the phenomenon called the galloping of the bridge under the wind loading, and cause what they call the negative, the aerodynamic damping. They say so. If you're interested on that, you can Google and research. And you will find that some engineer try to explain the collapse of the Tacoma Narrow Bridge by assuming negative aerodynamic damping. Okay, and that's why the vibration is very large and the bridge collapse. But normally we don't have this. Okay, let's look at the example, one of the example before the end of the chapter, I think. Yeah. The structural frame is rigid, jointed, and fixed on its support. You see, it has the mass M. This is the mass, 5,000 kilograms. And the columns assumed to be weightless, has the flexibility EI equal to 4.5 10 power 6 Newton meter square. Assume that the viscous damping or the damping ratio is 4%. Calculate the damp, the underdamped natural frequency, B, the peak displacement, and the first 5 cycle of the vibration, given that the beam is depressed horizontally 25 meters and suddenly released. Okay, we will go step by step for each question on this example. Let's start with the system like this. We can describe the motion by looking at only one degree of freedom. And that's why this system is endowed. It's a single degree freedom system. I can explain the motion of the system by putting only one x on the mass, on the centroid of the mass. And that's assumed to be x of time t. With this one, the equation of motion for sure, if you don't have any external force, you can imagine you can have something like this, right? Oh, I'm sorry, kx equal to 0. Okay? And the parameter m is 5,000 kilograms. Parameter c, let me do with the k first. K may be pretty easy, right? The k is like this, right? You have 2 columns. Each column has something like a 12 EI over H power 3. You look at the pink drawing. If you have the column like a shear mode motion like this fixed on the top of the column and the bottom of the column and let it go horizontally, you will have F over delta. This is the system number 1. F over delta is 12 EI over H power 3. But if you're talking about the system number 2, I do believe there has the different stiffness. It should be something like a 3. You know. Let's check with the Google, but I do believe like this. 3 or 4 EI. Check yourself. Okay. But in this case, the system is look like you have a very rigid mass beam. Therefore, the slope of the top of the column can be assumed to be fixed, right? No rotations. That's why you can assume number 1, the shear mode. And the stiffness K becomes something like a 2 multiplied by 12 EI over H power 3. Introduce EI equal to what? EI equal to this. 4.5 10 power 6. Then you obtain 4.0 10 power 6 as the stiffness K. Something like this, right? Could be Newton per meter. Am I correct? Okay, good. And the last one is about the damping C. Okay, let me calculate the damping C for you first. What do you see? If you would like me to write down the equation of motion, I need parameter M, K, and C. What is the C or the damping coefficient of this example? It is equal to, let me go back for you, just so you can know how to obtain this. We have the definition of the C and psi, not here and there. Yeah, here. Psi equal to C over 2m omega. Therefore, the C will be 2m omega psi, right? Okay. Should 2m omega and psi. you know M already. You don't know yet about the omega. You don't know yet about the precise no, right? Precise this. Damping ratio is called damping ratio 4%. This telling you about the precise equal to 0.04 already. So it's same. I have M, I have K, I have precise. I don't have yet omega. I need to calculate about the omega first. What is the omega? Omega is the square root of K over M, right? And when you introduce this, you will know the value of the omega, right? But this question, they don't ask us about the omega, they ask us about the frequency, but let you do it yourself. Not so difficult. Once you obtain the omega, introduce K and M like this, right? Take the square root and you obtain the omega, introduce the omega, M and precise, you obtain the damping coefficient C. If you want me to write down the equation of motion, now you can have the equation of motion you want. You know M, you know C, you know K already. Okay, but this example, what we interest is not MCK, we interest only the frequency, the undamped frequency and the damped natural frequency. The undamped natural frequency is like this: F equal to 1 over 2 pi square root K over M equal to 4.5 or 0 hertz. The unit is hertz. And the damped natural frequency is the frequency in which you're taking care the damping into account. And that becomes something like 4.498. We have these two frequency because the omega and the omega sub D are a little bit different. A little bit different because in the solution of the response X, you contain something like this, right? Normally your xt for the vibration is the e to the power minus precise omega t, and then multiply with the constant a1, maybe I call psi omega dt plus another constant a2 cosine omega dt. See, there's a omega d there and omega. They're quite different. The difference is about the damping, as you see in the pink letter, right? Omega and omega d. The difference is this term. This term. This term make the effect of the damping into account. Square root of 1 minus precise square. Normally, these two omega are very, very close. Almost the same. Looking at this example, even though we assume the damping of the system, damping ratio is 4%, 0.04. But the difference in terms of the frequency is very small. I can say this is a 4.5, this is 4.5, the same. The difference is very small. Only, how to say, 500 is about 4 in 500. 4 in 500, less than 0.1%, something like this, right? Or maybe just 1%, the difference. Very small in terms of civil engineering application. This difference is too small. But mathematically, theoretically speaking, they are different quantities. So we calculate and show them like that. Case B, they want us to calculate the vibration peaks. What they call the vibration peak is the thing like this. If you allow the system starting from x equal to, for example, a certain displacement, initial displacement, let's go like this, go like this, go like this. Right? Oh, not so cool. This is the peak. When we say the peak, positive peak, like this, like this. The maximum value in each cycle of vibrations. To calculate, so we write down the equations. I don't know how to say equation. E number 1. Right? To obtain E number 1, you introduce your initial conditions into equation number maybe 17. Okay, in the section of a 3.1 free underdamped system. You look at the general form of the free vibration solution and introduce the initial condition X. In this case, you can introduce the initial velocity to be 0. It means what? It means X dot 0 equal to 0. Once you introduce this X dot 0 equal to 0, you can obtain equation number E.1. From equation E.1, I do believe that the theoretically speaking, I should put the omega sub d, not just omega in the sine and cosine term, right? But as you see previously in the case A, we already showed that the frequency are pretty close, very similar, almost the same. Therefore, you might want to remove D if you want. This one, maybe you don't need to put omega sub D because practically the same, no different, right? Just omega is okay. And if you assume like that, you want to find the peak. When you want to find the peak, if you remember about the optimization, the thing is very simple. You perform derivative, right? You perform derivative and set it equal to 0. So that's why I perform one more derivative on the x, and I obtain the x dot of time t as in equation number E dot 2. And let E dot 2 equal to 0. Equation E dot 2, let it equal to 0 and calculate when it's happened. And you will find that it will happen when psi omega t equal to 0. Actually, if you look closely and introduce the value into equation number E1, maybe you can feel the same with me. It's 0.04, right? Psi function plus cosine. So the effect of the sine is only 4% compared with the cosine term. Therefore, the peak should occur pretty close to the cosine term. And when the cosine go to maximum, when cosine go to positive 1, it will happen when sine equal to 0, right? That's why you can have that the maximum displacement it occur when t equal to n pi over omega, like this. It's occur like at this time instant. And once you introduce n equal to 1, 2, 3, 4, 5, you can calculate the peak. You introduce t from equation number E dot 3 back into equation E dot 1. You can calculate the peak x equal to 19.44, 15.12, 11.7, 9.15, and 7.12 millimeters, respectively. Right? Okay, should be like that. And this is the one of the case of the building in Bangkok that we do the measurement to we put this is what they call the accelerometer. This one is the accelerometer. Oh, I'm sorry. accelerometer. So this sensor will detect the acceleration and convert to the digital signal. If you have the digital version, then if you still have the analog version, it provide you the voltage signal with time that is proportion to the acceleration of the building or the location you put the sensor on. Okay, based on this type of the accelerometer, when you put in the buildings, you can obtain the vibration and you can have the acceleration signal. And if you compute from the acceleration signal, you can know what's gonna be the frequency as well as what's gonna be the damping of the system of this building. And for example, this building is a landmark concrete building, and I think the starting height is something about 30. We have the period, and you see 1.6 along x direction, and we have the period of 1.5 along the y direction. The damping is very interesting. The damping ratio along the x direction is only 0.08. 0.008. That is 0.8%, right? This is a 0.8%, and this is 0.6%, very small. This is a real building, one of the real building in Bangkok. But if you look at the real measurement of the building, I'm not so sure in European countries. From the reference, I think it's most of the building in UK, Germany, in France, maybe. It looks like the damping ratio is as shown in this plot. The damping ratio, most of them, I think, most of them less than 2%. Right? 2%, 5% is there, and 10% is on. Right? Very small. The damping ratio for sure less than, of them, less than 10%, 0.1. But if you look closely, comparing between the RC building, steel building, it looks like the RC building has more damping than the steel building. And if you look at the building having height, I mean the story number or the height of the building, when it's taller and taller, the damping tend to be smaller and smaller. See, in very tall building here, the damping less than 2%, you see. Many of them less than 1% even. That's why in practice, many design code, they recommend to use, if you like under the wind loading for the RC building, they recommend the designer to use less than 2%. For very tall building, less than 1%. But for the earthquake, you can expect something like a 5%. Their proposed, their recommendation. The reason, the difference between, even my building are the same, right? The same building, but if I decide for the wind, I have only say a 2% damping ratio. But when I decide for the earthquake, I change to 5% damping ratio for the earthquake. The reason behind is something like this. For the wind, if you're talking about the specific wind small, so the motion of your building is not so large. That's why the damping is very small too. But when you consider the earthquake, most of the time when we design the building against the earthquake, we are talking about the extreme loading. So we can expect some cracks, some damages in the buildings under the earthquake. And because of that cracks, that might spread out in the whole building or in some lower floor of the buildings, the damping is increased. You can expect 5% as it's recommended by the design code. Okay, so this is chapter 3. Yeah, it could be end here. So far, if you have the question, this is the time for the discussion. Any from you? Otherwise, next time we will move on to the chapter 4. I think it's about the harmonic vibrations of the single degree freedom system. And that we'll discuss with you this coming Thursday. No questions so far?
Professor,
Yeah, please.
can you explain about equation E2 in example again?
E number 2.
Yes.
Okay.
How to use it?
You mean how to obtain E number 2?
Yes.
Okay. Equation number E number 2. I do like this, right? Do the d of xt like this. Perform derivative of equation E.1. You can perform that. And I do believe once you obtain the derivative of this term, actually I should have sine and cosine, right? But I think if you do so, you can have something like the cosine term. I don't know, alpha cosine term. This term could be very small. Comparing with the sine term. And you can, how to say, approximate it by remove this equation, remove this term. Okay. Let's try to check yourself, but I explained from E number 1 like this, right? You see there's a 2 term, sine and cosine, but the sine is multiplied by the cosine. This is 0.04. Therefore, this is 1.0, right, for the cosine, but for the sine term, you have 0.04. It's just 4%. So some might assume this one to be 0, very small compared with the cosine term. And if I assume like that from E number 1, the derivative of E number 1 will result only the sine here, right? From cosine, we change to sine like this. Very the same thing, I think. You do with the derivative first and remove the smaller term out from your consideration and say you just approximate. Or you will remove the first term here from the very beginning because you found this term will be very small compared with this cosine term, the pink term. The red term is smaller than the pink term, just 4%. So we can assume it's 0, something like this. Okay.
Okay.
Yeah. Any other questions? Okay, if you don't have any more questions, I would like to end my discussion today here and hope to have a discussion with you again on this coming Thursday morning. Okay, thank you and goodbye. Have a good day.
Thank you, Professor.